Great to see you all.
One thing, quick second.
Okay, cool. Hi, everyone. I'm super excited to talk about my research today. I'll be talking about enabling consistency in data selection pipelines with representation shifts. So when we typically talk about machine learning, we typically talk a lot about performance. That's why I want to start off by kind of giving us a feel of why consistency is important. And I'd like to start off with an example that I hope that a lot of us can relate to. Namely, I want to start off with an example in autonomous vehicles and show where consistency in machine learning pipelines can be particularly relevant. So what I'm showing you guys over here is a typical scenario that you would see in traffic, right? So imagine you have a car and you want to do object detection in this scenario. So we have the scene where we have a couple of cars here on the right. We have this van over here. We have a car in the back over here, and we have another car going towards us. And we have these two pedestrians that you can see over here. So we have one bicyclist over here, as well as another pedestrian in front of this van. So imagine we try to do object detection with a neural network. In the first round, you can imagine a software constellation coming up with these particular bounding boxes. So as you can see, the neural network is able to detect this car that you can see here in the front. It's able to detect the van and the car going towards us. It can pick up these two pedestrians, but we also get this false positive. So we detect a traffic sign here on the left as a pedestrian, right? Now, imagine we take this a step further and perform an update to the system. So this could be by, for instance, swapping out the architecture, by essentially tuning parameters, doing something here, right? And in the second round, we improve the performance. That's the idea of the update. So we start to detect this car in the front, right? We detect this car in the back, so the one that was further away. And we get rid of this particular, hi everyone. And we get rid of this false positive traffic sign that you can see here on the left. But crucially, right, what happens is we miss this particular pedestrian that you see in the front of the van over here. So even though we have an overall performance improvement by essentially doing a update to the system, there is some performance deterioration happening, meaning the performance is not consistent, right? And that's what I really want to take a look at today, because you can already imagine intuitively that if we do not detect this pedestrian, that the second software constellation can result in severe harm, right? So if this pedestrian runs out into the streets and the car hits the pedestrian, well, you'll first of all have a massive lawsuit, and apart from that, you're miles away from ever deploying this technology. So this notion of performance deterioration is actually really important to get these systems out into the real world. And it's particularly difficult because just by looking at these numbers that you see here at the bottom, you would imagine that going for the update is always a good idea. And that's what I really want to, that's really at the center of this talk today, namely what we call performance regression. So a performance deterioration after updating a model. So so far I've been mainly talking about updates relatively generically, right? So I've been talking about swapping out architectures, tuning hyperparameters, etc. But I actually want to really look at one particular update type in particular. And that is when we actually start talking about the data and when we update the data. And why I think this particular example of updates is particularly important is because when we look at data collection pipelines, it doesn't really matter if we look at industry or academia. It's always the typical standard is always to gather more data, to collect more edge cases, to gather as much as we can. And what you can see over here is the same phenomenon can happen, right? So if I have a small training data set and I achieve an accuracy of, for instance, 87%, and I start collecting a lot more data and increase the data set, increase the edge cases, increase everything, right? I might get a higher accuracy on the target distribution, but there may still be performance deterioration happening. And that's really what I want to emphasize in this talk today. And I'm going to be focusing on updates in data selection pipelines in particular, because software updates play a crucial role in data selection pipelines and should actually be integrated or are extremely important to assess performance and deployment decisions of neural networks. So in this talk, I'll be mainly focusing on active learning in terms of the data selection process, but I want to emphasize that all of this what I'm talking about is generally applicable to any data selection process. So that being said, I kind of want us all to walk away with three different things, right? I want everyone, once we're done with this presentation, I actually want three things to stick. The first thing is, what are the implications of consistency or regression in data selection pipelines and active learning? So what actually happens if I integrate this consistency aspect into data collection pipelines? The second thing I want us to walk away with is, why is regression actually happening? Why are neural networks inconsistent in data selection pipelines? And where are the different factors that really play into this? Now, the third thing I want us to walk away with is regression mitigation. So are there particular ways we can essentially address regression, right? Is there a way to reduce regression and improve the consistency of a neural network within the data selection itself? So that brings me to this particular outline that I have for you guys. And I want to really partition this entire presentation into three different parts. The first one is going to be looking at the background of regression. So what I mean with that is we're going to be looking at data selection pipelines, particularly active learning. We're going to be looking where regression happens within an active learning pipeline. And then we're also going to be talking about how we can even measure regression, right? So how can we even quantify this performance deterioration over updates? The second piece that I'm going to be talking about is this analysis part. Namely, I want to focus here on these influencing factors, right? Where does regression come from? That's the second takeaway message that I really want to instill in you guys today. And that's where we're going to be talking about that. And in the final part, I'll be talking about an algorithm that we developed, namely Curie, and it's part of this framework called positive congruent active learning. And it's a way, we essentially show that you can mitigate some regression happening within the data selection process. So let's get started with the background. So anyone who isn't familiar with active learning, this is where you should pay attention, because otherwise the rest of the presentation is really not going to be that fun. So pay good attention here. So this is a typical active learning workflow. The idea of active learning is to improve the data efficiency of a neural network by involving it in the annotation process. So the idea is to let the neural network choose which samples from a big unlabeled pool should be labeled to improve the performance the most, right? So imagine you have two different things. You have a lot of unlabeled data on the far left, you see over here. And then you also have a small set of labeled data, right? So you have humans actively label a small set that you see down here. The idea is we use this neural network, you train the neural network on the labeled data that you have. Then you take all of this unlabeled data and you push it through your network, producing and extracting these features you see over here, right? Now, these features from the neural network, you plug into an acquisition function. Now, what this acquisition function essentially does is it takes all of these features and all of these different samples, it ranks them from most important to least important, right? And the idea is we essentially take the ones that are the most informative, and those are then sent to the human to label, and then they're added to the training set. And then we iteratively keep on doing this until we reach a certain budget, meaning we have the maximum amount of labels that we can afford, or we top at some particular performance in terms of generalization. So now, where does regression come in? Namely in the selection, right? So if we're actually looking at where regression can happen, taking the model out of the picture, it's really at which samples do we select and how do they affect the update, right? And the way you can imagine it is we can select samples that result in a very consistent performance throughout, but we can also select samples that result in a very inconsistent performance, right? And the implications of this are actually pretty hefty, as you can see here on the bottom left. One thing is stopping criteria, right? So when do you stop this entire iteration, this process, right? Do I start at the latest round? That was, and imagine we have the pedestrian example that you saw earlier on, right? If we misclassified that pedestrian in the last round, but we classified in the previous round, we may actually want to go for an earlier round that you see, right? So it's not as simple as just going for the highest performance. Now, the second one is, when do we actually deploy a neural network in this problem, right? So when do we essentially finish up, and when do we decide that we want to deploy it? And the final one is, we can really assess these acquisition functions from a different light, right? So it's not only about improving performance, improving generalization performance, but also how consistent is our acquisition function throughout this process. So now I talked about what active learning essentially is. Now I want to switch gears and talk about how we can essentially measure regression. And regression or consistency is something that's independent of actually just that, data selection or active learning. And that's what I really want to go into detail over here. If I have a neural network and I update it from an old neural network to a newer neural network, right? There are several things that can happen. And I want to take your attention here to this example you see here on the right, sorry. You can see essentially two different classes, and this is a binary classification problem. So this dashed line represents the old neural network, right? And then we perform some kind of update, right? We perform some kind of improvement, and this new line over here represents the new neural network, right? The classification of the new neural network. And well, there are 4 different groupings our samples can fall into, namely both wrong, both correct, negative flips, and positive. So both wrong and both correct are actually very obvious, right? That means that the old neural network and the new neural network either had both correct or they had them both wrong. So both correct would be these green samples that you see here on the left, and both wrong would be these 2 samples, for instance. Now, where it gets interesting are the flips, right? So what can happen is we can improve our performance. Those are positive flips. That means we incorrectly classified them in the previous one with the previous model, and now we're correctly classifying. Those are the groups that you see up here, right? So this is the positive flip. Now, what also happens is the negative flip, and that's what you can see at the bottom of here. That means we correctly classified it in the correctly in the previous one, wrong in the current round, right? And these ones are essentially really what measure regression, right? They measure performance deterioration. And that's what I really want to emphasize here. And if you want to formalize it, it's very simple. It just means that the old model here, if we take this binary, if we take this binary equation over here, it's a binary variable. It reduces to 1 if the old sample or the old neural network was correct and the new neural network was incorrect, right? So that's when we have a negative flip. And that's what measures regression. So how can we build this into a metric? Well, very straightforward. We measure the ratio of negative flips that happen throughout the entire data, right? So if you take the entire, if you take the entire data set, you count all of the samples that had a negative flip, right? That's what you can see over here, and you divide it by the total amount of samples in the data set. Now, how does this relate to active learning? Well, the old model is the previous rounds, right? With the smaller data set size, and the new model is with the updated, bigger training set. And that's what I really want to show here on the right. So taking our previous example with this pedestrian, right? The current rounds neural network produces misses the pedestrian, as you can see over here. The previous rounds captures the pedestrian, and this one here we measure as a negative flip happening. And the negative flip rate would be the ratio of everything within the test set. So this is cool, right? This gives us a certain measure to essentially assess negative flip rate. And the way this really looks like when you do this in practice, this is a active learning run on Scifar 10 with these 3 different acquisition functions: entropy, leads, competence, and margin. On the x-axis, you can see the size of the labeled training data, right? So it increases over time. We're adding, we're annotating new samples and added to, right? And on the y-axis, you can see the negative flip rate. And in this case, it decreases over an increasing size of the training samples. So what I really want to emphasize here is higher NFR is bad, right? That means we have more negative flips happening, that means we have a very low consistency. So emphasis here being that it's not like accuracy where higher is better. So now that we kind of took a look at how we can measure regression and how it kind of fits into this framework of active learning, I kind of want to dive into these influential factors of what causes regression, right? And what effect it has on data selection process, right? And I want to look at several different things. But before we dive into that, let me kind of go for the expectation or what you would expect. If I increase the size of labeled samples, right, that means my representation or my model should consistently improve, right? It should be consistently gathering more information, meaning the representation becomes more accurate. And by a more accurate representation, you would also assume that it would be more consistent, right? It means it's not as dynamic anymore because we have more accurate representations. And that's really what I'm showing over here, and it's very similar to the curve that I just now showed. That means with an increasing accuracy, right? So the more samples we add to our training set, the better our generalization performance gets, but also the lower the NFR or the regression gets. So if you remember the CSIP 10 curve I just showed you, it was dropping with increasing samples. Now, what I want to convince you guys in the next couple of slides is that this actually in reality is the case. We can't really say how this regression trend actually goes because it's dependent on so many other factors other than just training set size. And what I really want to talk about are two different observations. The first one is that there are a lot of different factors that influence regression in data selection pipelines. And we'll be looking at class complexity and we'll be looking at data imbalance. Now, the second one is that we can create different subsets that essentially increase or decrease regression, right? And the second observation is going to be really important for our regression mitigation algorithm, right? If we essentially are capable of selecting subsets that are very favorable for regression. So that being said, let's dig right in. And I want to start with a class complexity setup, right? I want to start with a class complexity experiment. And what I want to do is I want to measure what class complexity or what effect the class complexity has in our regression pipeline. So if you look at our classical active learning workflow, which I have here on the right, the unlabeled pool being up here, the labeled training pool being down here, and this classical workflow that I showed earlier on, the idea is very simple. We take this data set CSIP 100 and we simply remove a set of classes. So making CSIP 100 CSIP 80 or CSIP 5, right? By essentially removing all of the classes from very specific classes, right? We're not very specific classes, but we remove a set of classes. Now, what happens if we do this, right? What I'm showing you here are two different sets of NFR curves. On the x-axis, once again, you can see the size of the labeled training set, right? And it increases when we add more data to the pipeline. And what you can see here on the top or on the left side are when we have 5 classes of CSIP 100. And what you can see here on the right side are if we need 50 classes of CSIP 100. So there's a really big difference in terms of class complexity that you can see over here. And what's interesting is on the left side, you can see that NFR drops over time. So that's the expectation that I essentially just mentioned just now. If we add more data samples to it, if we add more data samples, the representation becomes more accurate, it becomes less dynamic, we have a higher consistency. Now, on the right side, on the other hand, you see the exact opposite. By adding more samples to the data set, right, you're actually increasing dynamics in the representation and thereby essentially increasing the NFR that you see over here. So that's really interesting, right? That means it's completely going against what you would intuitively expect. And this kind of manifests also further in data imbalances, not only in class complexity. And I really want to show this also in terms of data imbalance here as well. And the experiment we're going to do here is actually also very similar. So if you look on the right side, once again, I show you the active learning workflow. And now we take CSIP 100 again. We first remove a set of classes, and then we imbalance the data set, right? Before essentially feeding it into the active learning workflow that you see here on the right. And just to really show, or at least kind of drill this down to give you guys a feel of what we're seeing in the next slide, I'm going to be showing you the class distributions here in the balance scenario at the top and versus the imbalance scenario on the bottom. So CSIP 100 is super balanced. Everyone who has ever worked with that thing, there are the same amount of classes for every single class, right? And in the training set, there are more samples. In the test set, there are less samples. That's what you can essentially see here on this top row. The x-axis shows the class index. The y-axis shows the number of samples that have that class index. Now, if we imbalance the data set, we do this in two separate ways, right? The first step is we reduce the number of samples for half of these classes. So we take half of them and we reduce the number of samples here significantly. So what I did here is I reduced it from, I think, 500 to 100 samples. So by an 80% cut. And on the test set, on the other hand, what we do is we essentially reduce the number of samples, but not from the ones that we reduced in the training set, but the ones, but exactly the opposite ones. And the idea behind this is to essentially have a lot of training samples, very few test samples, very little training samples, a lot of test samples, right? And by doing so, you get a massive imbalance. And I think you can already imagine what I'm going to be showing you here is a very similar thing, right? It completely reverses the trend. So if we look here on the left, I'm showing you with 15 classes. If we keep on adding samples to the training set, we get a reduction in NFR. And the moment we increase the complexity by introducing this imbalance that you see here on the right, it essentially results in this increase, right? That's a very interesting thing to look at. What's also interesting is if you look at the beginning, in these ranges, for instance, at 400, you will notice that the actual NFR value at 400 is actually lower than the value of NFR at 400 over here. Now, intuitively, this is because this data representation that you essentially see is severely imbalanced and may, for instance, not contain all of the classes in very early rounds. So the moment you start adding different classes to it, it adds a lot more dynamic. Whereas if it's completely wrong, it may actually result in mapping of the classes deep into the same manifold, resulting in a very consistent algorithm that you can see over here. So I just showed you guys different factors that really impact the trend that you see in consistency or regression. Namely, I showed you imbalance and I showed you class complexity, right? Now, what I also want to talk about, that kind of gives us this the first point I wanted to drill down, right? It gives us that various impact factors are impactful towards regression. It's not only labeled training set size. Now, the second thing that I really want to talk about are these different subsets. So the idea is that we want to find subsets that can increase the NFR or decrease the NFR, because we want to use these for our algorithm later on. So that being said, let's take a look at it, right? So what I want to do here is essentially define some subgroups and just sample from these subgroups to essentially show how the NFR changes. And to kind of make this a bit more clear, I want to kind of talk about the setup that I have over here. So once again, we have the unlabeled pool up here, the labeled training pool down here. We first train the neural network until convergence. Then we take this unlabeled pool and produce these features that you see here in the center. Now, the next part is we start determining these subgroups. And the idea behind it is that we determine these 4 different subgroups. We determine both correct, both wrong, negative flips, and positive flips that I showed you earlier on. So this is a hypothetical experiment because in order to determine all of these 4 subgroups, you need the labels. You need to know if my previous network was wrong and now it is correct, right? Or the other way around. So you really need these labels to essentially generate these. But we want to use this to kind of show what happens if we sample from these ideal subgroups. So we determine the subgroups by using the labels, and we use the network from the previous round. That gives us these four different subgroups. And now we pick one of these, right? So I'm going to be showing you four curves at the moment where each of these, where we just pick one of these. And then we use the acquisition function to essentially just pull from these particular subgroups. So you can imagine we take the entire data set, that's like 40,000, for instance, or the unlabeled pool, let's say it's 40,000. Then we take all of the positive flips, those are, for instance, only 10,000. And then we allow the acquisition function to just access those 10,000 samples. Now, what can we expect here? And this is actually really interesting, in my opinion. Let's kind of really take these graphs apart. So what I'm showing you is random sampling, right? So just randomly sampling from these subgroups. But what I'm showing you are these four different subgroups. So both correct, both wrong, positive flips, and negative flips, right? So the very first thing you can notice, which I was showing earlier on as well, there's no really clear, obvious thing that you could say towards a trend. In some subgroupings, for instance, this positive flips, you see that the regression increases over the size of the training sets, or in this blue setting, the both correct one, it also increases, whereas for the other two, it decreases. So that's the thing that I've been showing earlier on, but this also comes out over here as well. But what's interesting here is that are these two very fundamentally different behaviors, and I kind of want to point these out over here. So let's start with both correct and positive flips, right? So that means that the network was correct in both of these, and we have positive flips, meaning if the previous one was incorrect and now it's correct. You see that they're not very informative. So in terms of accuracy, they're lower than these other two ones, but they're actually very consistent, that you can see over here, right? So one reason you can think of this essentially is that these neural networks, if you consistently are giving it both correct and positive flips, it's going to be, you're not inducing a lot more information into the pipeline, which is why the accuracy is lower, because it's already features that it mostly already has learned. So the second thing that you can see is that in these other groupings, both wrong and negative flips are more informative, right? So they give you a lot more information in terms of generalization, but they also result in a higher NFR, right? Which also intuitively makes sense. If you have very highly informative samples, that will induce a lot more dynamic in your representation over the rounds, landing a very much higher negative flip rate at these beginning rounds. So what I really want to emphasize here, so these two things were interesting, but I feel that this takeaway is probably the most important. And that's, if you look at this orange curve and this red curve, right? Before you even know what I'm exactly showing here, you can see that in terms of accuracy, they're very much competitive. The red one is slightly better than the orange curve, but in these sections, it isn't even better than the orange curve. But you get a significant reduction in terms of negative flip rate, right? That means by selecting the appropriate samples, there is a lot of potential here to essentially reduce negative flip rate while maintaining accuracy or even improving accuracy, right? So that kind of brings me back to this original slide that I had over here. We kind of went through these two conclusions. There are various impact factors that influence regression, and that data subsets exist that can increase or decrease the negative flip rate. And I already mentioned it in the last slide. This means there's actually potential here to build an algorithm that reduces the negative flip rate, right? By essentially selecting appropriate data. Which brings me to the last third of this talk, which is regression mitigation. So is there a way we can reduce the negative flip rate while maintaining accuracy? And the idea in this is actually very straightforward. And that's what we call positive congruent active learning. And the idea is we want to reduce regression while maintaining accuracy. So if I may direct your attention to this diagram you see here on the right, given this unlabeled data pool you see here at the top, you simply input it into the active learning strategy in standard active learning, right? The idea of positive congruent active learning is we take this data pool and then we restrict it to some kind of subset. So think about like the negative flips or the positive flips or whatever that we just saw, right? That we restrict it to a subset, and then we only use that subset to input it into the strategy. So the key here is kind of this, if you formalize it, right, we formalize it with this Q function you see down here. So this is conventional active learning. This is the equation I showed you in the acquisition function box earlier on. It essentially takes an acquisition batch and it ranks it. Now, what it's based on is on this unlabeled pool that you see down here. Now, by introducing positive congruent active learning, the idea is to restrict it, meaning we essentially introduce this function Q you see here down here to essentially reduce the sample size of the unlabeled pool. So the question, how do we kind of design this pool? And in order to do that, I want to switch gears and then bring it back to the Q function in a moment. So the way we're going to be doing this is, as you can probably already guess from the title, with representation shifts. And I kind of want to emphasize what I mean with representation shifts. And I want to do this with this notion of switch events that you can see over here. So a switch event is very straightforward. You have two different models, right? Imagine it being from one round and the other round, or from one epoch and the next epoch within a round, right? The idea is you take these two different models, right? And you take the same sample, you feed it through both of these things, right? And if the prediction switches between both of these models, we count that as a switch event. So in that sense, fairly straightforward. If you have this toad, for instance, the current network predicts a frog, the previous network predicts a fly. That's a switch event, right? If you want to formalize it, if you have a prediction of a neural network, which you define as y, it's basically a binary variable that reduces to 1 if they're the same, or it's 0 if it's not the same. Right? So that's the idea behind it. And then you can use the switch score that you see at the bottom here. If we measure these in epochs, right? If we measure it across the entire training run, you can essentially imagine you just sum up all of the switch events that happen for a given sample across the entire training run. So let me kind of emphasize how this fits into regression, right? So using the same example I just had earlier on, these switch events really quantify flips, right? They quantify the combination of both positive flips and negative flips, to be very precise. So if you take this example where we had where I basically showed you all of these different classes between both correct, both wrong, negative flips and positive flips, the switch these samples over here are a switch event, and these ones down here are switching samples, whereas the rest of them are 0. So that already gives you an intuition that they're very much relevant for for regression, right? And that's what we're really going to be using here in this positive congruent active learning workflow. So that's where I want to define this Q function you see here down here as just the minimum switch events, right? So if you take the switches and you minimize them, that intuitively already gives you a sense of that less representation shifts will be happening and resulting in ultimately also less regression, has the potential to reduce regression. And if I want to define this in terms of math, the Q function of this D pool is essentially minimizing the sum over all of these, over all epochs, these switch events for each of these samples, and we take the samples with the least amount of switch events, right? A certain amount of these samples. That gives you this function you see down here. And we call this congruency under regression instance estimation, or CURI, right? So how does this fit, or how do we connect the dots? How does this fit into our active learning workflow I'll just show you guys? The idea is we train the neural network, right? We train the neural network. During this training, we essentially evaluate switches on this unlabeled pool. So you have to imagine we train one epoch, we essentially do inference on the entire unlabeled pool. Then we train another epoch, do another inference set. We compare those two predictions and count switch events. Then we take the smallest amount of, or we take a certain amount of samples from the smallest amount of switch events. So we really take, let's say 1,000 or 2,000 of those samples, which is also defined by this hyperparameter phi that you see over here. We take the smallest amount, we take the samples with the smallest amount of switch events, and that really starts restricting our data pool into the smaller subset. We input it into this acquisition function, and then we can keep on retraining. So it's basically a plug-in approach on top of any different acquisition function you can think of, by essentially restricting the data pool before inputting it into the acquisition function. So how does this perform? And I have two more slides here where I'm just going to be showing you what happens when we use this technique, and then I'll open up for questions. So what I'm showing here on the left is the accuracy plot for this X-ray data set. And on the right, I'm showing you the NFR plot for that data set. So y-axis is either NFR accuracy, x-axis is the size of the training set, right? And what you can see over here is on the left, by you adding Curie, for instance, to entropy, you don't really see a statistically significant difference in terms of accuracy. You even get a slight hike at the beginning over here, right? But more importantly, you see that the NFR usually consistently stays under the original entropy curve, and partially even by a significant amount, as you can see over here. So there are some settings where this Curie works very well. And there are also settings where it's not as effective. Well, it's still to some extent effective, but maybe in the wrong areas you would want it to. So for instance, in CSIP 100, you can actually see this performance increase in terms of accuracy, right? So the blue curve is the original entropy curve, the orange curve is Curie, right? And by adding this to this entropy curve, you can essentially see an accuracy improvement. Whereas the negative flip rate also starts decreasing over at the end, but it actually results in a small hike at the beginning. That is partially due to that at very early stages, the representations are a lot more dynamic, and that results in a lot more noise in the switch event metric as well, which can essentially also result in an NFR increase in the worst case. So yeah, that already brings me to the end of this presentation. So the work that I just presented is we submitted it, so you can't read it yet. But these other two, if you're super interested in what I'm doing, please take a look. Yeah, that's pretty much it. Are there any questions on this? Thanks for listening. Cool. Yes.
It's not a question, I just have.
Yeah.
This was very easily understandable for a non-ML person. Like my background is in CS, but nothing with machine learning or training models or anything. So this was, I like how you stepped through everything, and I think I learned a lot. I'm a design major, so I'm always thinking about colors too. And for some of the like graphs, there are rationale for like the color you choose when you're depicting like. It was just a couple of steps where I think regression was, or no, accuracy was increasing over time, but it's popping out red to me, and I'm like, okay, is this bad? But I'm listening to you. It's just conflicting with my mind. But I know that's like a nitpicky thing, but is there a rationale for like already in the community, what colors you use? Is that a stupid question?
No. So in terms of the colors that I was using with the curves, they're actually very random. So this is done with matplotlib, and I just randomly assigned the colors. It didn't have any meaning in that case. It was just pretty arbitrary.
So you'll probably be giving this talk to people who actually like know about this stuff, so it won't matter to them. But when I'm trying to track and like follow things in my mind, I'm like, okay, this is what I'm looking at. But it's like changing all this.
No, that's really, thanks so much for the feedback. That's super helpful, actually. I'll in general, I feel like I have to make my graph more consistent. It's for feedback. Thank you very much.
So, okay, never mind. Anyone online can also ask questions. Does anyone in the room have any questions about what Ryan said or anything like that?
They got a chat message.
I know, but it was not relevant. So. Okay, then. Well, give a round of applause for Ryan once again to help him to that you did a good job and I'm proud of you and everything like that, but.
I take you serious.
Why can't I take? But yes, thanks everyone online for coming as well, and we'll have another one in 2 weeks. It'll be the last one of the semester, but yes, once again, thanks Ryan, and that concludes the seminar.